Okay? So why is this my favorite chapter? Because all semester I've been telling you, unlike Physics 1, where we started with F equals ma rather quickly, we only had built up to it for a couple weeks, and then we sort of saw its applications. We had to build up to our central equation the entire semester. And this is the chapter where we finally get not our central equation, mind you, but our set of equations, which are the Maxwell equations. Now, I'm going to talk briefly about magnetism of matter, but you will not be tested on magnetism of matter, and you will not be, it's just sort of a fun, calm down part, and we'll use it to sort of probably close out the day. I'm thinking we can get most of this or the week. I'm very confident. I wouldn't be surprised if we got through all of this today. And that's because there's not a lot of examples. We're constructing the Maxwell's equations, and there's not a lot of applications. The applications for Maxwell's equations are electromagnetic waves. And all of chapter 33 is about the applications to this chapter. So this chapter is the theoretical framework and the density current, not the density current, the displacement current, and how Maxwell's equations were formed. And then once we see them, I'm going to show you some math tricks, and we're going to do some elegant derivations instead of the asinine derivations the book does. Because the book goes through this derivation that is very long-winded, is not intuitive, and is not actually helpful for understanding more advanced electromagnetic theory. It is not the way we do electromagnetic theory. So I have chosen to chuck it. But that being said, we want to build up our Maxwell's equations, but I want to look at the story so far. Okay? And I'm not going to look at these learning objectives here, but I'm going to use the white space to make my point. So we have three basic laws that help us out here. All right? We have Gauss's law, which applies for both electric and magnetic fields, right? So we have E dot dA. Since this is an area integral, you will sometimes see this written as two integrals to separate it from a line integral, but you're just supposed to get the context through the nature of the area vector. And that is equal to Q over epsilon naught. And then for magnetic fields, we always have a dipole. So we have B dot D A equals 0. That's a statement that there's no magnetic monopoles. But of course, in order to make this true, we must have that closed integral. Now, we have, which one do we have here? The next one is, we had Ampere's law. B dot ds, right, equals mu naught I. Hold on. And then we had something rather interesting. We had the integral of E dot ds. And again, these are closed paths. It's equal to minus dB dt. And that was Faraday's law, right? Okay, so this is sort of the story so far. And these are our, and right now we have sort of three sets of equations named after three very prominent physicists, right? So this would be Maxwell. No, sorry, Gauss, one of the most famous mathematicians of all time. Ampere, right? So important that current is named after him. And Faraday, one of the most successful experimental physicists of all time. But notice Faraday discovered that an electric field can be created by a changing magnetic field. So this is where our story is right now. But you'll notice we'll have, with one modification, so we'll make a modification, and then these 4 equations plus that modification will be the Maxwell's equations. All right? So now we have to figure out why these are all, because right now these are all separate equations, right? The only one that's Ampere and Gauss seem unrelated. The only one that starts to hint that there's some sort of connection is Faraday's law. Okay? So let's look at what we've seen so far, and we'll look at some more examples of this. Yeah, Caesar. Oh, did you have a question, or did you just join the session? Can't. Oh, no problem. Yeah. Oh, okay. So, right, no battery or sources needed. Well, wait. Oh, Tuesday's good. Oh, you asked that a while ago, Lewis, but that's okay. So when we look here, we have these sets of equations. So let's take a look at what we've been looking at. We can see Gauss's law here for magnetic fields. Any closed surface, Gaussian surface you draw, you're always going to start at the North Pole and end at the South Pole. All right? And when we look at Gauss's law for magnetic fields, it's basically a statement that if we cut up magnets, right? This magnet has a north and a south pole. If we cut it up into parts, each other little magnet has a north and a south pole. There's no way to have a North Pole only magnet or a South Pole only magnet. And in classical physics, magnetic monopoles do not exist. In quantum physics, they are possible, but the universe has, the quantum electrodynamics says the universe need only have one. So, good luck finding it. But we're not doing quantum electrodynamics, we're doing classical electrodynamics. And so that's what we are looking at here, right? And we can see for any classical magnet, we always have a north and a south pole. And I want to show you the difference between this and when we used when we did magnetic flux, because you might be saying, what? Magnetic flux was not always 0, but the magnetic flux for inductance, we would write the integral of B dot dA, right? We would not, you notice there's no closed there. So when you're looking at that magnetic flux, let's make the shape. So if for instance we only looked at the magnetic flux here through this circle, all right, you'll notice that we're not going through a surface area. We can just look at it through the loop, right? And say, it's just going through the loop. But this is not a surface area. It's not simply connected. There's two sides, right? One to the other. There's no way to get there without sort of flipping orientation. Whereas if you draw a sphere, right, or a cylinder or some sort of Gaussian sphere. Oh, Lordy, I'm trying to move things. Which is what they're doing here. You'll notice that if you can sort of imagine that as a sphere, let me draw it with a pencil. Right? You have, if you look at the surface area of the sphere, you have just as much coming in as going out, so the net flux through the closed sphere, the closed surface area, is going to be 0. Okay? So that's all this busy slide basically says. All right? Now, we want to look at induced magnetic fields. All right? So they do this, they sort of give away the cat and mouse here. So if we look at the integral of B dot ds, you're going to notice here that it looks a little funny. We just wrote a minute ago that the integral of B dot ds is equal to mu naught I. Right? This is Ampere's law. But you'll notice when we look at Faraday's law, we find that this electric field, right? This induced electric field, if you will be due to a changing magnetic field. So what Maxwell thought is, why can't you also have a sort of a mirror process, if you will, where you have a changing electric field resulting in a magnetic field. And so Maxwell proposed this sort of version of Ampere's law, all right, where he invented this term here. All right, and we're going to call this the displacement current because it's a displaced current. All right, but the idea is if we have, say, when charging a capacitor, as you charge the capacitor, this field gets bigger and bigger and bigger, right? And so as that field gets bigger, is it possible that that changing electric field will actually induce, as it grows, a magnetic field that you can measure and behave like a current? So we want to look at this idea of an induced electric field, and you'll notice that they diagram it out here, and it looks a lot like the induced EMF, where you have this circular closed magnetic field. So basically, what you should do is if this is true, if Maxwell is correct, you should be able to measure, as the capacitor is charging, you should be able to measure a B field while the capacitor is charging and discharging. But then when it's fully charged or discharged, B will be equal to 0. All right? So we already did that. Now, but as I pointed out before, we already have Ampere's law. So in essence, when you combine Maxwell's term and Ampere's term, right? This is Maxwell's term. This is Ampere's term. You get sort of this combined law, all right? And what this does is it sort of describes, you know, when the capacitor is charging or discharging, you have current flowing through the circuit, and you go from one form to the other generally, all right? But again, this is a little weird, and you're going to notice that they call this a fictitious current. And it's a fictitious current because you can't put an ammeter inside a capacitor and measure a current, but you can measure the magnetic field. So that's what makes it a little weird and eerie. And it's a very big insight, all right? And that current is called the displacement current, okay? And I'm not sure why they teach the Ampere. This is my first time using this edition. I'm going to have to switch that in the future. I didn't realize that. We should talk about displacement current before we talk about Ampere Maxwell, because you'll notice that you get, even though you get to see where this displacement current is coming from, we define the term, and when we plug it and look at this as a current, this displacement current, and plug it into the Ampere Maxwell law, although it does look like I drew these, I did not, you get this sort of more clean Ampere Maxwell law indicating the enclosed current and the displacement current, all right? Where the displacement current is circled by that integration loop, that Amperean surface. This doesn't seem like much, but this is one of the most crucial observations of the 19th century. And in fact, it creates an entire bridge. It doesn't seem like it, but this whole idea, if you think of physics as an arch, right, from the Greeks, then you had Newton build stuff. And how do you get from the Greeks and Newton to quantum physics and general relativity? There's a connector stone, and this displacement current is the connector stone. And it might be one of the most, it's counterintuitive, again, because if we go back and look at our capacitor, right, we have something, we're going to see, we have something that looks like a current magnetically, but won't have a current measurement. It's a huge insight, all right? And this insight that that came from Faraday's law, which is also a big 19th century discovery, which is that if changing magnetic fields lead to electric fields, then maybe a changing a changing electric field will lead to a magnetic field. All right, so that created these, the Ampere-Maxwell law and this nicer version of it. But this particular object here, this displacement current, you'll notice only matters on how the electric field or the electric flux changes with time. Okay? So as we go forward, this is what I was sort of waiting to. This is the good one. So you can see before charging, all right, let's go, we'll talk through these figures. Let's look here. Before charging, of course, there's nothing going on, right? There's no magnetic field here. Now, during the charging, magnetic field is created by both the real and fictional currents, all right? So again, the displacement current can be looked at as sort of this charging of the capacitor. But you'll notice you have a current here, right? And that will lead to a magnetic field. You'll also have a current on the other side of the capacitor that will lead to a magnetic field. And you will have a magnetic field at the capacitor. But you'll notice there's no current here. That's what's called fictitious. So it's this different or displacement current that causes this magnetic field. Now, during charging, the right-hand rule works for both the real and fictional currents. All right, and after charging, there's no magnetic field, right? Because there's nothing happening. There's no change in here. So if we look here, we can find that outside of the capacitor, the magnetic field will just be equal to B over ID. Or wait, why does it? Oh, no, I was looking at something. You can use Ampere's law, and you'll notice that to find these magnetic fields, you're just using Ampere's law. Let's look here, or the Ampere-Maxwell law. So if we look here, we can see that the integral of B dot ds is going to be equal to mu naught epsilon naught so we're just going to look at inside, right? But you'll remember that we called this term the displacement current. That term is equal to ID. So therefore, we can rewrite our Maxwell law as B. That D should be much smaller. The subscript. ID B dot ds. We want to close those too. It's going to equal mu naught I displacement current. And now you can use the Ampere-Maxwell law just like you could before, but now you'll notice that instead you have this displacement current, right? And this displacement current will be given in terms of that electric flux change. So you can see how it goes from each level. And like I said, what's weird, again, is that if you put a current meter in here, you're not going to measure anything. But you will measure a magnetic field if you put a magnetic field sensor right here. And that magnetic field sensor will come from this, what we call fictional current. All right. So once we make that modification to our the Ampere's law, then the collection of equations is collectively known as Maxwell's equations. All right. Now, you might be wondering, well, what's the big deal? Why does he get credit when all he really did was add this part? That's a good question. The Maxwell's equations become very connected. Once you add this term, everything becomes incredibly connected. okay? And you can use these to describe pretty much all of classical electromagnetism. So everything we've learned and everything we haven't learned. And I've got to tell you guys, we have not learned a lot. So we're going to look at one key result here, one of the biggest results. And in order to do that, we're going to have to look at some vector calculus. All right? So I don't feel terrible about it, but Maxwell's equations have the integral forms we saw and these differential forms. Now, I want to make the differential forms make some sense, so I'm going to do just one. And basically, there's three things we have to know: the divergence theorem, Stokes' theorem, and a vector identity. So I'll state the vector identity when we need it, but I want to show you at least how to get one of these. So we'll just do Gauss's law, and I'll convert that to differential form for you so you can see how it goes. But basically, the divergence theorem and Stokes' theorem allow you to transfer surface integrals to volume integrals and whatnot. And they're very, very powerful mathematical theorems, but I realize you haven't learned them yet. But I'll show you how one works in action, and you can look up the rest. They all kind of work the same way. So if we look here at our Gauss's law, actually, I don't want to start it there. I'm going to start it back here. Right, E dot dA is equal to Q over epsilon naught. Now, when we look at this, Q, you'll recall that Q can be simple, but it can also be as hard as a volume integral, right, over a charge density times the volume dV, right, where this would be a dx, dy, dz. This would actually be a triple integral. But you can write it this way. And this is a constant charge density. Now, one thing we have to understand is when we do vectors, we're going to want to understand that we have this del or nabla symbol, okay? And this is a vector itself, and when you use del, it is just a three-dimensional partial derivative. Okay, no big deal, just a way of looking at multiple derivatives and keeping everything three-dimensional. One thing that I don't like about our book in particular is we do things in 3 dimensions until we need to actually explain something, then we simplify it, and we'll sometimes make it more complicated to explain something in 1 dimension, whereas because of the nature of the electromagnetic field, it actually just flows much better to do this in 3 dimensions. So I'm not asking you to understand this, but it's just a map operation. I think you understand what all these are. And you can sort of, this I'm hoping makes a bit of sense to you. Just a more compact way of writing all those derivatives is with a del. And I'll often write it without its symbol. I'll just write it as an upside down triangle. I'll try and make it better than this one. So that one will be deleted. That's what I've just explained here, Lewis. The upside down triangle is that squared. It's this vector part. Basically, if you have a function, right, of f, let me show you an example. If you have an f, some function f of x, y, z, a multivariate function, del f is going to be equal to df dx in the I hat direction plus df dy in the j hat direction plus df dz in the k hat direction. Yeah, a gradient vector. That's exactly what it is. It's the gradient. So now to look at this, we can rewrite our integral up here. I'm going to clear everything and rewrite or I'm going to rewrite this integral over here. We can write this as equals the volume integral of rho dv. So the divergence theorem is just a theorem that states that we can turn this surface integral into a vector integral by replacing E dot dA. So we can replace E dot dA. We can say this is equal to the volume integral of del cross E. Oh no, wait a minute. I'm messing this up here. This is the divergence theorem, not Stokes' theorem. That's what happens when you haven't done vector calc in 20 years, folks. See, and that del dot a vector, like del dot E is the divergence of E times the volume. Okay? So now what we can do, I'm going to clear all this. And we're going to rewrite Gauss's law in terms of vector integrals. Or volume integrals, I'm sorry. They're already vector integrals. The volume of, hold on, del dot E dv, that's going to equal the volume integral of rho over epsilon naught, right, times dv. Now this is interesting. You have the same integrals on both sides. So what you can do is you can rewrite this. You can move this to the other side, right? So you subtract those two integrals. It would basically look like this. Without rewriting it, I'm going to delete that. And I'm going to say equals 0. I've just moved that integral onto the other side. All right? If they're equal, you can always do that. Yeah? But now they're both volume integrals, so I can actually write this as the volume integral of del. Some of you probably already see it, but I got to be honest, I'm just trying to do right by the mathematicians. Minus the charge density over epsilon naught dv equals 0. And why do I do this? Because if the integral is equal to 0, then the integrand, everything in the parentheses, must also be equal to 0. And therefore, this implies that del dot E must equal rho over epsilon naught. And as you'll notice, that's our first differential Maxwell equation. Okay? So using vector theorems that work in just the same way, it's the same process, you can turn those integral equations into these differential forms of the Maxwell's equations. All right? So what we want to do is we will notice something. We're going to look at magnetic fields, how magnetic fields and electromagnetic fields interact in free space, right? In the vacuum. And you have to remember, we talked about in the very beginning of the semester, we talked about the wave equation and waves, where if we had a wave y, or a wave f, right, d2 dx2 equals 1 over v squared dt2, right? But all these waves needed mediums. And now light was already sort of established to be a wave, but the nature, like what light is made out of, what it looks like, wasn't known. And the first major result of Maxwell's equations was to see if we could sort of sieve out the nature of light. And you'll see here we can rewrite Maxwell's equations in free space. So in free space, there are no charges. So del dot E will be equal to 0, right? And we already know del dot B is equal to 0 because there are no magnetic monopoles. All right. We have del cross E is equal to minus dB dt, right? And then because we're in free space, this part goes to 0 because there's no currents, there's no charges. So then we have del cross B equals mu naught epsilon naught delta E over delta T. Now there are two results I want to look at. Well, we'll do them first. Actually, no, there's a minor result we'll look at that will help us with the next chapter, and then there's the major result of this chapter. Okay? So what we want to do is we'll need to make use of one particular vector identity, and that is this particular vector identity. All right, del cross a vector, let's call it A, just to be equal to del, hold on, getting confused. I'm not getting confused, I'm just writing the wrong thing. When you take vector calculus, you will be required to prove this definition, and it's a crucially important identity to prove. But since this is physics, we're just going to accept it as fact. Okay? So we want to keep that in mind as we go forward. All right? Now, so these are Maxwell's equations in free space, and we want to be able to work. What we're going to do is we want to derive our wave equation, and I'll show you how this goes. So let's write them a little smaller in free space here. Del dot B equals 0. Del dot E equals 0. Del cross E B equals mu naught epsilon naught dE dt, and del cross E equals minus dB dt. All right, so let me just let me make sure I'm not off by any signs, because a sign error will, I think I'm good. Yeah, okay. So going back here, we have those, and so now what we want to do is we will, in order to take the curl, all we have to do to derive the wave equation is take the curl of, I don't know why I keep messing up these triangles. The curl of B. Okay? And you'll remember that we can write this using our vector equation, that the curl of the curl is going to be equal to the gradient of the divergence minus the second derivative, or the Laplacian, of the field, the B field, okay? So when we look at this, we can look at our free space equations, and we already see that this part goes to 0, right? So we can write this as equal to minus del squared B. Okay? Okay. So we should be good there. And what we also want to look at here is that we want to recall that del cross B, right? Or rather, hold on, let me look at something here. I just did this before class. I don't know what, and I'm already confused by my notes. All right. No, this makes sense. So del cross E, as we'll recall before, is equal to minus dB dt. All right. And if we look at this, we can see that del cross E, right, is going to be equal to we're just making some replacements here. So all we're doing is using our Maxwell's free space equations, and we're doing some vector calculus. So the vector calculus, of course, will be confusing because you all haven't learned how to do that yet. And I'm flubbing it up because I'm getting my B's and H's. I did it in terms of H and D, but I thought that might be confusing, and it is. So if we look at that, we can say that this is equal to we can look at that and say that that is equal to hold on. How did I mess this up? Hold on. This is embarrassing. I can't read my own handwriting. And I knew I needed my own handwriting because it got confusing. And this is obnoxious. All right. Hold on. That's not helpful. Let me look at my own work here for a minute, because I had this all figured out. Okay, so that's that. But del cross E equals negative B. That's true. So del cross E is equal to, right? Right. Ah, okay. Got it. Okay, so if we look here, it's equal to this dB dt, but we'll notice that we can write this as dB dt. No, that's redundant. Hold on. Del cross. Oh, I see. Hold on. I'm going crazy. Again, it's vector calculus, so no worries. And like I said, we're really far ahead. So I'm not terribly worried about it. Okay. It's the problem with doing math. So if we look at this, we can see this as equal to this del cross dB dt. We can plug that in, and we would get, because of the way these work, we can get minus I'm just going to write down my algebra. Minus mu naught d dt of del cross B. Oh no, wait a minute, that mu naught's not there. Because again, I did these in terms of displacements, which is not smart. All right, you know what I think we're going to do? I think we're going to go on a little bit of break because I'm tired of fumbling my way through this, and I had this all figured out just so that this wouldn't happen. So we're just going to go on break because this is the big thing, and it's turning into a cluster muck. So we'll meet back at 7, and I'll redo this so it makes sense. I think I have you all at the free space equation, so I'm going to go through the derivation, and then we'll do that when we get back. All right, so we'll see you at 7, and we'll come back and do it. It's not complicated. I'm just tired and my brain's getting crossed and I'm forgetting basic things. So let's start again with our free space equations. So remember, there's no charges. Del dot B is always equal to 0. Del dot E is equal to minus dB dt, and del dot B, or sorry, cross is equal to mu naught epsilon naught dE dt. Okay, so we have our differential Maxwell's equations in free space, and we're going to look at del cross B, and that's going to equal, so the first thing we're going to do is use our identity. And we get that is equal to del. So all we've done is use the identity. We have the second derivative part. And we can say that that's equal to, because this part goes to 0, as you can see from your Maxwell free space equation, this is equal to minus del squared B. Now, looking at that, we can see here that it'll, for the same thing, this will be equal to minus del squared E. Okay, so we can see for the same vector, identity applies, and we are fine. Now, we can look at this. We also want to note, if we look at our del cross E, del cross E, we want to take a look at this one. All right, so del cross del, it's drawing these triangles wrong is really throwing me off. All right, but if we look at this part here, we can look at our Maxwell free space equations, and we can say that this is equal to del cross minus dB dt. All right, that's just all we've done is used, I'll change colors. We've just used our free space equation, then I'm slowly circling here. And we've replaced it with our del cross E. Now, another way to write this is equals del cross minus d dt B, where the derivative operates on B. Now, this is where I was getting confused, and this is why I'm going to say it's not complicated. It looks complicated, but it's really not, because we know from our properties of cross products that we can factor out the minus d dt, and we can write this as minus d dt del cross B. So not hard at all. Okay, and then del cross B, we can look up here and use our fourth Maxwell free space differential form equation, and we can replace that on the other side. We can write this as equal to minus d dt I forgot those constants. mu naught epsilon naught dE dt. Now keep in mind here, your E's are your electric fields and your B's are your magnetic fields. So this simplifies to minus no. Minus mu naught epsilon naught d2t dt2. No, hold on. This is when I know my dysgraphia is starting to really act up. d2e dt2. Okay, so what we can see now is looking at both sides of the equation. We can write that minus del squared E, right? Because that's equal to del cross E is equal to minus mu naught epsilon naught dt2. And what you'll notice is if we take this to one, remember a few things. So remember that del is equal to d dx I hat plus, it's the gradient vector, right? d dy and the j hat plus d dz and the k hat. Now that we have this is a general wave equation. And it will look familiar if we just look at the first part of this, right? If we just look at the first part of the gradient and we cross off these minus signs, we get d2e dx2 equals mu naught epsilon naught times d2e. And now this takes us, the reason we write it like this is because now this takes us back to the first chapter almost of the semester, right? The wave equation. And so now we sort of end where we've started. And you can do a similar analysis and get a similar result for B, for the B field. But I want you to notice something. Our original wave equation for wave F, right? We had df2, the second derivative, spatial derivative, is equal to 1 over v squared of the second times the second time derivative. And this was true for all waves, right? You might remember that from earlier in the semester. So the claim that we have here then is that 1 over v squared equals mu naught epsilon naught, our permittivity times our permeability of free space. And so we can predict that the speed in vacuum of this wave should be equal to 1 over the square root of epsilon naught times mu naught. And you will notice that, and very surprisingly, is equal to c, the speed of light, which you could experimentally measure before. So that means that light is an electromagnetic wave. All right? And as you can see, it's a little complicated. I realize we're not doing a lot of vector calculus, but I did only need one screen to do it. It's not that complicated, and it's really about making the correct replacements. And then what I just was not, I did two things. I did it by hand in terms of D and H first, thinking I would save myself some time, but that didn't help. And then I was just not seeing the cross product relation in my head. All right, that's why I focused on this step. This is the step. This is the one step that was thrown me for a loop before break. Don't know why I couldn't see it. It's actually the simplest step and the one that everyone should be able to see, because we can just pull that out from the cross product and rewrite it like so and get our curl here. All right. And then once you have this step, it's all very trivial, because you just replace del cross B with the time-changing electric field on this side, and it simplifies down to here. And our vector identity will give us this second spatial, our Laplacian times our, but that's the Laplacian is just the del, the second derivative, the second gradient, our del squared E, and we can equate those two things transitively, and we get our wave equation. Okay? And again, this is a huge important result, because now you can solve this differential equation with boundary problems. Yeah. So first step, we'll even do it in a different color. So the first step on one side is to look at the these triple curls, or these curls of curls. All right, so you'll notice we do it for E and B, right? Now here we just use the vector identity, which we can see here in 1. And we can look at our Maxwell free space equations and see that del dot B is equal to 0, right? So then we're stuck with just that this left-hand side equals this Laplacian, or this del squared B on the right-hand side. The similar thing holds true. You'll notice del dot E is equal to 0 as well. So the relationship holds for the electric field in free space. If you're not in free space, you'll notice I say that a lot, things can become complicated, because if you're in a conductor, del dot E is not equal to 0. But that's not what we're looking at right now. We're looking at in free space. What do we expect to happen here? So that's the end of one side. That side was very easy. Now we want to investigate this vector triple product coming from another route. We're going to notice that we can look at this del cross E, right? So this is step 3. So I'm going to write plug into 1. We're going to plug into 2. And you'll notice here we're going to plug into 3. Right? Where this is step 3. It's a little bit more of a clear 3. Right? And so from here, we can plug into 3. Instead of del cross E, we can write negative dB dt. That's what we have here. All right, and now we just rewrite this in a different way. So we're going from, to go from red to blue, we're just doing a rewrite, right? And then we're using our basic vector properties of cross product to factor it out of the whole cross product. And then we get, so this is just chapter 3 stuff, really. All we're doing is using our properties from chapter 3 to get this equation and write it down. And now, that we have it, that we've rewritten this at the end of 3, we can write, we can go to 4 here, right, where we'll plug into 4. Okay, and when we plug in del cross B from our Maxwell's equations equals mu naught epsilon naught dE dt into 4 here, we get this expression, which can simplify down into this minus mu naught epsilon naught times the second time derivative of the electric field. Okay? Yeah, chapter 3 cross product. So this is, so now we have the left-hand side of the equation, and we finally get from 3 and 4 to the right-hand side of the equation. But we can see that del cross E is equal to del cross E. So so step 5 is writing them like this and canceling the minus signs, and then you get del squared, or the Laplacian, times the electric field, or the second gradient of the electric field, is equal to mu naught epsilon naught times the second time derivative of the electric field. And then you have step 6, which is a 1D version, right? One dim version. So this is the specific case of this general equation, okay? And we see here, this was a, this was just a recognition. This is not a step. This is just, we're looking back and noting that our equation, 6, is a wave equation by definition from chapter 16, okay? And then we also have another part too, which is not, which we're noticing from the wave equation. You could call this step 7, I suppose, if you want, where we're noticing v of the velocity of the wave is equal to 1 over the square root of mu naught times epsilon naught. And if you plug those into your calculator and take that square root, you're going to find that it's equal to the speed of light. And the speed of light was experimentally determined, all right, before. So this conclusively proves not only that light can travel in free space, but what its velocity in free space should be, and it's the speed of light. All right, it's 1 over c. So that's pretty exciting. And again, if you apply certain boundary conditions to these waves, or to the wave equation, you get to solve for all sorts of exciting things like waveguides and attenuation, and all sorts of weird stuff that you can do. The depth and complexity grows quite rapidly. But this is a real physics result. And it's a really good one too. And like I said, this is a huge connector to get to modern physics. And I want to talk a little bit about that because that's usually what I would do at this point. Because we're essentially done with the Maxwell's equations themselves. And like I said, Maxwell's equations allow you to describe an electromagnetic wave, find its power, talk about polarization, and all these things are chapter 33. So there's no need to do them, and there's no really example to do here, because very much this is the example I want to do, right? This is what I wanted to show you. And I have no idea why my brain shut down or got stram-noodled, but it did. So this is, the math is a little beyond you. I hope that from 7 o'clock on it makes some sense. I understand that it wouldn't before. But what's important to note now, or the conclusion we can come up with, is that changing magnetic fields, right? And I won't talk about magnetic fields here, but we can see here that a changing magnetic field, hold on, actually I'm going to put it in type. And we also see that okay. Now I often say that if you've taken Calc 3, you have all the mathematical sophistication required to derive the special theory of relativity that Einstein derived from Newton's laws. It takes no more sophisticated math than that. No techniques are needed outside those first 3 semesters of calculus. However, seeing the physical connection is quite difficult. All right, it doesn't just follow. So I want to show you what some of the implications are of these two statements that we've just seen are true. We've spent the whole semester now building up to see that this is true. So I want you to do a thought experiment with me. I want you to pretend that my doodle pen here is a train. And if you can think about it, imagine that you are sitting in the train holding a ball of charge, right? This charged ball. If you were in a wizard book, you could throw it at someone and hurt them with it, right? But it's this charged ball that sort of floats that you're holding in your hand that's not hurting you. You're just holding this charged ball. And I want you to imagine that someone next to you has a magnetic field sensor. Okay? Now, one of the principal questions this asked, these Maxwell's equations created a huge problem in physics. Because you'll remember where I'm going. If we turn off the charge in the ball, you'll remember in physics 1 that if you throw the ball up and down, someone inside the train who could see in will see the ball just go up and down, right? But someone who's outside the train will see it go like this, right? They'll see it translating and going up and down. It'll have sort of a triangle thing going on here, right? Like, so the person in the train will see it go up, down, up, down, up, down. The person outside will see it go something like this. Okay? But we all agree that it left my hand and ended in my hand, right? Where there's certain things we agree on that happened. And if we're looking through two inertial frames, we can do a Galilean transformation. Now, here's where this gets interesting. Imagine you have that charged ball again. Now, if you have it in situation A where you're in the train and you're just holding the ball, let's make two situations down here. As you look with your magnetic field probe, right, with your ball of charge, we'll call that negative. It's just standing there. There's going to be this is going to measure 0. However, if you're outside and you see the train going by, you see this ball of charge has a velocity. If it has a velocity, right, I is equal to dq dt. Right? And we know that from the Biot-Savart law that B is equal to I times L, or IL cross R hat over R squared, right? So we know that if we have a magnetic field or a current, we're going to have a magnetic field. So out here, you would measure B. So now the question is there a magnetic field or isn't there? Who's right? In one train, in one picture, there is no magnetic field. It does not exist. In the other picture, there is a magnetic field and it does exist. Who's right? Well, it's either there or it's not. How can you have a Basically, I want you to think about this. Well, they're interrelated, but how they're interrelated is very difficult. But I want you to think about it this much, from this sense, to see how weird it is. Imagine that you have your fridge, right? And one person says that your fridge magnet will be attracted to that charge, and the other person says it won't. That's how weird this is. That's a little different than a change in path. And in fact, Maxwell's equations are not consistent with Galilean transformations because of this very problem. This was a huge problem in physics. When people say, oh, people thought physics was done, nobody who was serious about physics could have possibly thought it was done. Transformation equations were developed to reconcile this, and you came up with Lorentz transformations. But the physical, it was hard they looked more abstract than physical. And it took Albert Einstein to make them physical and to make the observation that the speed of light, in order for the Lorentz transformations to make physical sense, that the speed of light had to be constant in all reference frames, which is a huge physical leap. That's not a mathematical thing. Well, basically what we find, and we'll see this will make a little more sense in when we talk about the next chapter, but basically there is no such thing as a magnetic field or electric field when it comes to light or this kind of charge. There's electromagnetic fields, and they have an E axis and a B axis. And whether you're moving just depends. I'll change color to purple. Any vector can have a little bit of electric field and a little bit of magnetic field. And in the case of the car moving, you transform this vector so that it's only along the e-axis, which means b equals 0. But now when you're moving, that vector gets transformed into, it's sort of like a rotation, if you will, or a boost is what they end up calling it, where now you have a little bit of electric field and a little bit of magnetic field. So now you measure a little bit of magnetic field here. But if you were to take the Pythagorean theorem part, if you will, that electromagnetic magnitude will always remain the same. Okay? Now, one of the other big results from here that we are going to use very frequently, if we go back, I want to go back here. So if we look here at del cross E equals minus dB. Can't do a B tonight. I can't do anything right tonight. Minus dB dt, yeah? You'll notice when we do that, we can make this into one dimension and sort of look at this as dE dx. Equals minus dB dt. Okay, and this will be important for getting one of our big results for the next chapter. That they sort of use their what do you call it? The integral asinine way of developing this relation. So we want to look at it here. You can look at it this way. You can also see that if you look at del cross B, this will be equal to we'll start here. Hold on, did I? No, yeah, del cross. Anyhow. Anyhow, we can see from those differential forms, for instance, del dot. Yeah. Again, getting tired and going crazy, but that's okay. You can see that del cross E is minus dB dt. And we just want to focus on these ones for a little bit in free space. And what we want to be able to do here is actually use these as spatial derivatives to relate our, sort of look at these as first derivatives. In special versions where we can look at our curl and just write it this way and relate this to our we can relate this to our, let me, yeah, dB dx equals mu naught epsilon naught dv dt. So we'll be able to relate these first derivatives to each other, and we're going to see that when we look at and get our solutions, once we use that in conjunction with our other result, 1 equals the square root of mu naught epsilon naught, we're going to be able to see that we can actually relate, once we understand a little bit better. We're sort of, because when I looked at the next chapter, they sort of just state this without proving it. So you can use the proof and sort of see from here that E over B will be equal to 1 over C squared, I believe. Hold on. Yeah. And they use that quite a bit. No, wait a minute. I got that wrong. E over B is equal to C. I'm just making all sorts of mistakes tonight. This doesn't have a lot of context yet, but we can use these sort of, from the differential form, we can get these kinds of equations pretty easily. And we're going to be making use of this fact in the next chapter heavily. But let's end the night talking about magnets and going over permanent magnets and the tie and sort of magnetism in nature beyond electromagnets. So the Earth is a magnet. You'll notice that the I believe they get this part wrong, because the geomagnetic North Pole is supposed to be the North Pole of the magnet. I don't know, this is the South Pole of the magnet. So when you have a compass, right, your north aligns with the South Pole because it's attracted to it, and vice versa, right? So this is one of those weird things that a lot of people disagree on. But anyway, the Earth is a magnet, right? And compasses give us a, let us measure that pretty directly, which is something we would have done in lab, but we're not there. So we want to look at the types of magnetism in matter that occur. And fundamentally, magnetism, and most basic part, has to do with the spin of electrons. All right. So when we have the spin magnetic dipole moment, that's a way of looking at atomic spin. But none of this means anything because we're not learning about quantum physics yet. This really only makes sense in quantum physics because spin is purely quantum mechanical. But we'll have to understand the existence of this intrinsic spin, like intrinsic charge or intrinsic mass, to understand the nature of magnetism. So all we need to know for now is it exists. All right. And we can see that stuff. Again, these are orbital. So we want to learn about the 3 types of magnetism. We have diamagnetism. So a diamagnetic material, that if it's placed in an external magnetic field, develops a magnetic dipole moment directed opposite the external field. All right. So if the field is uniform, the diamagnetic material is repelled from the region of greater magnetic field and toward the region of lesser field. All right. So in this sense, almost everything in the universe is diamagnetic. All right. You are diamagnetic. This little frog here is diamagnetic. And essentially, you'll notice a frost here. There's such a strong magnetic field from the superconductor that it's lifting the frog quite evenly and comfortably. It's elevating the frog. All right. This is one of those things, like, this is the technology sort of behind hoverboards, right? The idea is that if you had a superconductor, you can make the diamagnetism, you can make the applied field strong enough, the external field strong enough to lift you from the field. Okay. So when we look here, so this little guy is just elevating. He's floating. No, the little frog is very happy. He's just being elevated. He's quite comfortable. The forces act evenly on his body. Now, paramagnetism is a little different, right? So if a material is placed in an external magnetic field, develops a magnetic dipole moment in the direction of the external field. So in a paramagnetic material, if the field is non-uniform, the paramagnetic material is attracted toward the region of greater magnetic field from the region. All right. So paramagnetism and diamagnetism have to do with how you react to an external magnetic field. All right. And they're both fairly weak. You need very strong external fields to sort of get those properties going. Ferromagnetism, this is what your permanent magnets are based on, right? And so you have these spins sort of going towards one way. And you can change these regions to change the poles of a magnet. That's possible. I also would have shown you that in lab. But if you look here, it tells you that the ferromagnetic material placed in an external magnetic field develops a strong magnetic dipole moment in the direction of the external field. Now, if the field is non-uniform, the ferromagnetic material is attracted towards the region of the greater magnetic field from a lesser region. So it sounds like paramagnetism, but again, it's based on a net field from these regions, and it explains permanent magnetism. Okay, those are ferromagnetic. So you can see all of those. So that's pretty much it for magnetism. The big part of this chapter was the Maxwell's equations and the displacement current. And I'm going to take the picture of the attendance, and then, you're free to go. So, hold on, taking the picture. Man, everything's kind of a disaster tonight. Okay. All right, so take it easy. Think about those implications of Maxwell's equations. They are very cool, despite my kind of craziness in doing them and my vector mistakes. But they are very, very good. No, not today. Not today. Today I haven't eaten anything yet. Maybe that's the problem. So yeah. So hopefully you have good weekends. Again, that stuff will be up soon and coming soon. So did someone have a question? Repeat the discussion you had about the labs and the final exam. Sure. So the final exam, like I said, I think Lewis already asked for the Wednesday. I can be pretty flexible. My preferred day would be Wednesday the 10th, but I don't need to have it that day. So if a lot of you are finding that you have a Calc 2 final on that day, I would be up for moving it. But everyone's got to kind of want to move. We have to appease as many as possible, but keep in mind we can't make everyone happy probably. So that's my starting day for then. As far as labs go, the new lab is going to come out tonight or tomorrow. I've already designed most of it. I just have to record the instructions, and I'm going to give some written instructions too for this one, I think. With the tasks I want you to do. And then that will be due June 8th, and there's going to be a 50-point extra credit lab that's going to cover optics. Okay, so that will also be due June 8th, but that probably won't come out till the 22nd, like a week from Friday. So we're done with 32, and we still have a day left. We're going to make some serious headway into 33. So I expect us to be done with chapter 33 sort of by the time by the 19th, the day before your exam. So that's chapter 19, and when we're done with chapter 33, that will be the end of what you'll be tested on for the course. All right, so we're basically done with the third quiz. I'm going to go on teaching because optics is a part of this course that generally gets cut out. I am going to lecture optics. You will have an extra credit optics lab and an extra credit optics homework. Okay? So I really want you all to focus on doing as well as you can on your labs, but do those extra credits so that you can, any points you may have missed or any points that might not be worth it to go back and revise, you can just get. Okay? The extra credit lab is just going to be a discussion. I don't need an abstract or all that stuff. Just write a quick discussion of what you measured, what you did, and all that stuff, and like a page, you know. So real simple, not a big deal. Okay, and everyone will get, and whoever, you know, basically if you turn it in and your safe assign score is low, I'm gonna give it a quick read, and as long as you know it makes sense, you'll get full credit. Okay. So do those things. Get those grades as high as possible, because that gives you the maximum flexibility on the exam. I'm going to stop recording.